This is a continuation of Chapter 3. It's going to focus on details pertaining to the quantum mechanical model of the atom, which is the most recent model and the one that's accepted today. And specifically, we're going to talk more about what exactly is an orbital and how we define the orbitals using what we call quantum numbers. It's really kind of abstract, so this one you're going to have to really pay attention to and perhaps listen to more than once. Alrighty, so in the last lecture we talked a little bit about Bohr's model of the atom, where with Bohr he knew there was a nucleus, the subatomic particles had been discovered, and Bohr's primary contribution was that he said electrons outside the nucleus can only exist in particular energy levels. That's shown by the ends here in this wonderful drawing I just made. That's called quantized electrons. That was his major contribution. It turns out to be true. So an electron outside a nucleus cannot just kind of willy-nilly go where it wants to at a certain energy level. There are predefined energy levels that they exist in. There was still an issue with Bohr's model. Number one, he said that he believed electrons rotated about the nucleus. They absolutely do not. So please make sure you understand that. We don't know exactly how they move, but they do not rotate like a planetary model. And scientists were also not able to explain why the electrons remained stable in the particular energy level. So there was more work done. And the next couple of slides are going to go over additional key contributions that various scientists made to the Bohr model to get us to the quantum mechanical model. So we had, back before Louis de Broglie, scientists, Einstein, one of them, had declared that light can behave either as a particle or with wave-like properties. And depending on the model that you chose, you could learn different things about light. And so we call that the dual nature of light. Louis de Broglie proposed or hypothesized that particles containing mass, including the electron, could also have a dual nature. In other words, also sometimes behave as a particle, sometimes behave as a wave. And so de Broglie kind of merged Einstein's equation on relating energy to the speed of light and mass, and then Planck's equation relating energy of light to its frequency, and came up with de Broglie's equation. We are not going to do calculations with de Broglie's equation, but I do want you to understand some relationships that come out of this. The first, most important one, is that he is theorizing, as turns out it's supported with additional scientific evidence, that everything that has mass is also associated with a wavelength, okay? And so it turns out that like even you and I or a car or whatever, we have mass, right? So we're associated with a wavelength, but the theory goes that our wavelength is not observable because our mass is so large and it's in the denominator, right? Which means our wavelengths are infinitesimally small. But if you get something really small like an electron with a teeny tiny little mass, their wavelengths are going to be large enough to indirectly observe. All right, so that was a huge leap in development of the quantum mechanical model. So we went from Bohr's model to de Broglie's model, saying, okay, I agree with Bohr that the electrons are in particular energy levels, but now we're going to assume these electrons are associated with wave behavior, and that wave behavior has to be compatible with the energy level they're in. And so scientists began working on calculating the wavelength for electrons at a certain energy level. The next scientist who contributed something significant to the quantum mechanical model of the atom was Heisenberg. You may have heard of the Heisenberg uncertainty principle, but the bottom line is simply by observing the electron. Okay, so how do we observe things? Well, human beings, we shine light on them and try to look at them, right? It turns out you can't really do that with an electron, because the instant you hit it with light to illuminate it, you have affected its behavior. You've given it momentum. So the bottom line is, Heisenberg said it's basically impossible to know simultaneously the velocity or momentum of an electron and the position, not just an electron, any subatomic particle. So simply by this observing it, we lose information about it. So, because of the Heisenberg uncertainty principle, scientists said, yeah, we can't pinpoint exactly how an electron moves, while at the same time knowing exactly where it's located. So the only thing we can do is estimate the probability of where an electron is most likely to be found around an atom and what energy it's most likely to have. And so everything else we're going to talk about, the electron, you can see there's a lot of vagueness to it, and that's because of the Heisenberg uncertainty principle. So along comes Schrodinger, the last key scientist to contribute to this model, quantum mechanical model of the atom. And he basically wrote out long mathematical equation for the wavelength of electrons in atoms. And if you Google Schrodinger wave equation, there are these incredibly long, I don't even include it here, crazy mathematical equations. This guy was a genius squared. And then when he solved these mathematical equations for the wavelength of electrons in an atom, he came up with regions of space which describe the most probable location of an electron. Okay? These regions of space that tell us where an electron is likely to be found are called orbitals. So, what is an orbital? An orbital is simply a region of space, so it's not a physical thing that we can touch and investigate. It's simply a defined region of space where the probability of finding an electron in an atom is highest. Okay? Region of space where the probability of finding an electron in an atom is high. So you're going to see kind of some funky diagrams like this that show orbitals. Some people draw orbitals with hard lines like s orbital, p orbital, but really they're kind of fuzzy lines where the most dense regions in this electron dot diagram are the most likely location and energy level for an electron. Alrighty, so we're not going to really use these probability electron dot maps, and I have to apologize for when I imported this PowerPoint into my program here, the formatting is funky, so I'll have to change my formatting, but hopefully you can still read it okay. All right, so what we're going to use to describe orbitals are just these simple physical shapes. You may remember from high school chemistry, an s orbital is spherical in shape, and that just spherical around the nucleus. So it's kind of, well, it is assumed that the nucleus in all of these orbital drawings is in the center. P orbitals are dumbbell shape. And D orbitals are, most of them are clover shape. So they have 4 lobes, like 4-leaf clover. And there's one that's kind of funky, but we won't worry about that. So probably the only orbital shapes that I would ever ask you about on an exam would be S or P, as far as like identify this shape. There are F orbitals also, but their shape is so complex we don't try to draw them. So the rest of this lecture is talking about quantum numbers. So now that we've defined what an orbital is, as you can imagine, there are many, many different types of orbitals depending on their energy level, how far away they are from the nucleus, and a bunch of other properties. But how we specify specifically what orbital we're referring to is by using quantum numbers. So think of quantum numbers as an address, just like you would say, I live at 121 Cambridge Court in Ackworth, Georgia, zip code. So it's kind of like that. So this is just a picture, and it'll become more clear. This may blow you away in the beginning if you've never done quantum numbers, but I promise you, you will get it eventually, okay? So as I said, there are 4 different quantum numbers. Every single electron in an atom needs its own unique 4 quantum numbers to differentiate it from all of the other electrons. So the first quantum number, the most important, is n. That stands for the principal quantum number, and that correlates exactly with the energy level that the electron is in. N equals 1 is the energy level closest to the nucleus, and n increases as you get farther and farther away from the nucleus. And so you can see if we compare a 1s orbital to a 2s orbital, the electrons in a 2s orbital are likely to be farther away from the nucleus and of higher energy than electrons in a 1s orbital. The second quantum number is abbreviated with in italics L. It stands for the angular momentum quantum number, and L describes the shape of the orbital, okay? So you can see down here that if we're talking about an s orbital, L is assigned a value of 0. If we're talking about a p orbital, L is 1. If we're talking about a d orbital, L is 2. And I'll just add on to this, if we're talking about an f orbital, L equals 3. Why they can't just say SPDF, I don't know. So you have got to understand this correlation between the value of the angular momentum quantum number and the letter designation we use for the shape. Now, I do want to throw in here that primarily L is used to describe the shape, but it can also be thought of as an energy sublevel within each primary energy level, energy sublevel. So within, let's say, n equals 1 energy level, you'll see that we have L values of 0. And, well, it changes as we go higher and higher in n, which you'll see. But I want you to think of the L values of sublevels within the primary energy level n. I also want to point out, and this will come into play a few slides from here, that the values that L, angular momentum quantum number, is allowed to have range from a value of 0, that's where the first value always starts when you're talking about L, and proceeds in integers up to the highest value that L can have is n minus 1. So let me give you an example. Let's say we're in the 3rd primary energy level. We're n equals 3. What are the values, and L is going to be a sublevels here. So what are the values that L could have in the n equals 3 energy level? Well, looking at this list up here, L can have a value of 0. That's always where you want to start. And that is an s orbital. Remember, if L equals 0? L can also have a value of 1. So that's talking about the p orbital. And the highest value L can have is n minus 1. Okay? In this case, since n is 3 that we're talking about, that should be n minus 1, not n equals n. So 3, if n equals 3 and minus 1, so the highest value that L can have is 2. So that's the highest value when n equals 3. So here L can have a value of 2, which means we would be talking about a d orbital. So that'll be important later on. This is just kind of what I said. In the last page, you need to memorize that if you're talking about an s orbital, L equals 0, etc. All right, the third quantum number is m sub L, magnetic quantum number. This is a funky one to understand. It's defined as describing the orientation of an orbital in space. This is where I wish I was in person. So s orbitals are spherical, right? So imagine holding a ball that's one color, so a handball or racquetball, okay? You're holding it in your hand and there are no marks on it. If you close your eyes and rotate that ball in your hand and open your eyes back up, you will not be able to tell that you rotated it, okay? So s orbitals or anything spherical can only be oriented one way in space. No matter how you rotate it, it's going to look the same. Okay, so that means that, well, I'm getting ahead of myself. Let's take a different example. Let's talk about if L equals 1, so that's a p orbital. And remember, p orbitals are figure 8s or dumbbell shape. If you imagine a graph, right, with the XYZ axis, you can imagine that the p orbital might be oriented along the y-axis, the x-axis, or the z-axis, right? So there are 3 possible orientations for a p orbital. Now to spend a minute defining the limitations for the values of m sub L. You see here that its values vary from negative of whatever the value of L is to positive whatever the value of L is, moving in integers. So let me give you an example. Let's say that L value was 0. So we're talking about an s orbital. What are the values that m sub L could have if L is 0? Well, look back over here. M sub L varies from negative L, so in this case, that'd be negative 0 to positive 0, right? So the only values m sub L can have if L is 0 is also 0. Let's do one that's a little more meaningful. Let's say that L had a value of 2. So that would be talking about d orbitals, right? That would mean that m sub L could have a value. Now you're going to start at the negative L value, so negative 2, and you're going to move up in integers. Negative 1, you always have to go through 0 when you're talking about m sub L values. Then we have positive 1, and finally we have positive 2. All right, so those are the possible values for m sub L. Alrighty, the final quantum number, and it's an easy one, so breathe a sigh of relief on this, is m sub s. Be careful, remember there's an m sub L we just went over. So m sub s is the spin quantum number, and there are only two values that it can have. It either has a value of +1/2, which means an electron has an electromagnetic field that spins clockwise, or the ms value can have a value of -1/2, which means the electromagnetic field the electron puts off spins counterclockwise. That's it. It's one or the other. Here's a summary of the information, and if I were you, I would either jot this down or print it out or something to have it handy. And you definitely are going to need to work worksheets on quantum numbers to get comfortable enough with them. All right, so I'd like to give you a visual outlook on quantum numbers also. So let me walk you through this. You may prefer this over the previous slide that had them written out in kind of table format. So if we are energy level 1, so that's the orbital closest, or the energy level closest to the nucleus. The allowed values, so I'm going to call this the shell or energy level is N. The subshell or sub-energy level would be L. And the specific orbital would be M sub L. There we go. Think of them like that. So if we're in energy level 1, N equals 1, the values that L can have are only 0. Remember that L always starts at 0, that's a 0, and progresses in integers up to a maximum value of n minus 1. Well, 1 minus 1 is 0, so the only value L can have is 0. And if L is 0, M sub L is automatically 0. Just kind of a reminder, M sub L values can go from minus L, they progress through 0, and then the maximum value of plus L. I'm going to put the limitations above them. That might be helpful. L goes from 0 to a max of n minus 1. Alrighty, let's go to a more complicated. Let's go to energy level n equals 3. So if n equals 3, what are the values that L can have? Well, it always starts at 0, so every single energy level starts with an S sublevel or S orbital. That's the lowest energy one. Then the L values progress in integers by 1 until they get to a maximum of n minus 1. So if n equals 3, 3 minus 1 equals 2. So that means the maximum value that L can have for n equals 3 is 2. So we have L equals 0, S orbital, L equals 1, P orbital, and L equals 2, D orbital, if we are in n equals 3. I don't know if you remember this from high school, but here's a really simple way to state all that. The energy level 1 only has S orbitals. Energy level 2 has 2s and 2p orbitals. Energy level 3 has S, P, and D orbitals. And energy level 4 has S, P, D, and F. Okay, so now you're seeing kind of the ramifications of those limitations. And what's also handy to remember is energy level 1 has 1 sublevel. Energy level 2 has 2 sublevels. Energy level 3 has 3 sublevels. All right, almost done for here. Here's a sample one, which I'm going to do for you, and then I want you to go and try some on your own. What are all of the sublevels that are present when n equals 4? Okay, so if n equals 4, what are the values that L can have? Okay, so we can have L equals 0, L equal 1, L equal 2, and L equal 3. So in the n equal 4 level, we can have S orbitals, P orbitals, D orbitals, and F orbitals. All right? Those are the subshells. So you think of L as subshells or sublevels. Okay, now, how many total orbitals are there? Well, when you're talking about specific orbitals, you are talking about the M sub L value. So if L equals 0, if we're talking about an S orbital, M sub L can only equal 0, which means there's only, I don't know if you can see that way, there's only one orbital in the S. S sublevel only has one orbital. Let's look at the P sublevel when L equals 1. What values can M sub L have if L equals 1? Well, M sub L can be -1 it can be 0, and it can be positive 1. So there are 3 orbitals in a p sublevel. This may be ringing a bell. Okay, we'll see. We need this information when we do electron configurations. When L equals 2, what are the values that M sub L can have? Well, starts at minus L, right? So we can have minus 2, minus 1, 0, plus 1, and plus 2. So D sublevels have 5 orbitals. And finally, F sublevels, seeing a pattern here, 1, 3, 5, how many sublevels do you think F has? It has 7. Okay, I'm not going to draw those out. But you just go from minus 3 all the way through 0 up to plus 3, and that is 7 orbitals. All right. Here's one for you to try. So I would suggest turning off the video and tell me which of these combinations of quantum numbers, A, B, C, D, or E, is not possible, okay? So you've got to go over the rules and tell me which one isn't possible. So turn it off, try to do it yourself, and then come back and I'll go through it with you. All right, let's see. If an energy level 1, it's perfectly fine to have an s orbital, L equals 0. That goes okay. Energy level 2, we can also have an s orbital. L equals 0 means s orbital. Whoop, that's a mistake. Okay, that would be 2s orbital would be the right way to describe. If n equals 3 and L equals 0, that is, yes, a 3s orbital. If n equals 3 and L equals 1, that is describing a 3p orbital. If n equals 3 and L equals 2, that is describing a 3d orbital. So the rest of them are correct. The wrong answer is C. Let's try another one. Which of the following is not allowed combination of quantum numbers? So again, I suggest you turn off the video and try it yourself. All right, let's check this out. N equals 4. I'm going to start writing. L equals 3. What type of orbital are we talking about if L equals 3? That is an F orbital, right? And so we're talking about a 4f orbital. So now, is this M sub L value allowed? So remember that M sub L goes from minus L up through 0 all the way to positive L. So an M sub L value 3 is perfectly acceptable if L equals 3. So that one's okay. Let's look at B. B is talking about a 1s orbital. And is it okay to have a designation of M sub L equals 0 if L equals 0? Yes, it is. Now C, N equals 5. So that's what the big number is first. We're starting to do electron configurations. I'm kind of prompting you to get ready to do them. And L equals 4 is talking about what type of orbital? Let's see. 0 is S, 1 is P, 2 is D, 3 is F, 4 is G. Now, you're going to say, I never heard of a G orbital. And that's because they're considered excited state orbitals only. So most stable atoms don't have them, so you don't really have to worry about G's. But all right, so we are talking about a 5G orbital. Is it possible for M sub L to have a value of minus 2 if L equals 4? Yeah, it sure is. So that's actually okay. All right, D. Okay, we are talking about a 2, energy level 2. When L equals 1, that is a p orbital, so that looks cool. And M sub L equals 0 is perfectly fine if L equals 1. Alrighty, So we haven't found any mistakes, so hopefully our mistake will be in E. Let's see. N equals 3. L equals 3 means we're talking about an F orbital. Guess what? There's no such thing as a 3F orbital. Let's go back on the limitations to L. L can have values. The maximum L value is n minus 1. Oh, why do I keep putting equal? Okay, n is 3. 3 minus 1 is 2. So the highest value that L can have here is L equal 2. One last one for you to try. I'm going to give you a shortcut on this one. I think we were supposed to answer this on the last one. I may have forgotten to. How many possible orbitals are there for n equals 4? So I'm going to show you the long way, and then I'm going to show you the short way. Okay, so remember this is the main energy level. This is the sub level of energy. And now we're going to do the m sub L values, which are the actual orbitals. So this is what this question is asking for. It's asking for the number of orbitals. So if L equals 0, m sub L can only equal 0, right? And there's only one orbital. If L equals 1, m sub L can equal minus 1, 0, or plus 1. So I'm going to write here 1 orbital. So this is 3 orbitals. If L equals 2, m sub L values can be minus 2, minus 1, 0, plus 1, plus 2. So there are 5 orbitals there. If L equals 3, m sub L values can be minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. There are 7 orbitals in that one. So you add all the orbitals in the energy level n equals 4, and what do you get? 16 total orbitals. All right, that wasn't too bad, but it wasn't really fun. But if n equals 10, oh my gosh, that's way too much work filling out the total number of orbitals. So I'm going to give you a massive shortcut. The number of orbitals equals whatever n is squared. So, for example, if n equals 4, the number of orbitals is 4 squared, or 16. If n equals 10, the number of orbitals is 10 squared, or 100. Aren't you glad you didn't have to do that the long way? So that's a good little thing to remember. I would jot that down. That is it for this PowerPoint. And the next one is going to be electron configurations.